parallelism. This level parallelism, we can see this is the agenda of our class, on our course. Okay, I ask teacher tell me in university, in three students, all of you had a examination in our semester. Probably in 20 or 21 week, we will arrange online examination for the foreign students. So she tell me I must arrange 3 examinations, one for you, one for foreign students, one for next semester. So in this semester, our course will exam.
Why for next semester?
No, online examination probably in 20 or 21 weeks.
Yeah.
We are waiting for the planning. So our course will end in 17 weeks. So 20 or 21. From 17 to 20 is not wrong. So I will arrange the examination. The examination details I will give the teacher home.
So our 3 students examination will at 17 weeks, right?
No, please.
I said that we have three examination will held at 17th week, right?
No, not in 17. From 18 to 21. Yeah, we are arranged by teacher home.
Oh, okay.
If I have information, I will tell you.
And when you will provide us your suggestion?
Because the 17th week, we are class. We aren't ending the course. So from 18 to 21, this period.
Understood.
Yeah.
And when you will provide us the suggestion?
Yeah.
The suggestion.
What?
You told that for examination you will give us suggestion, like select some question. Suggestion.
What is suggestion? What is suggestion? Yeah.
Like you can give us some question and select
some 题目.
Yeah,题目.
Okay. When I prepare the examination, I will give you some Okay. Let's begin. In this 21, in lecture 21, we can see the 5 sections. We can see introduction, parallelism, and plate toxin, and SIMD architecture, and loop unrolling, and summary. Okay. More flow. We have talked in former class. We can see more flow every 2 years. The number of transistors on a chip of fixed size doubles. The important word is doubles. So you can find more flow. The trend is become large and large. So every 2 years, number of transistors can be doubles and doubles. So this is the trend. This is the trend. Okay, processors kept getting faster. We can see from 1975 to 2015. We can see from MIPS, Intel and AMD. From this and this point to this point, this period has a single core CPU. If we find this from 2003 to 2015, you can see from this period, this is double core CPU. So you can find the frequency. The trend is become big and big. From this to this, the trend is slow. So what's the reason? Because the CPU has 2 cores, 4 cores. So from the cores, divide some cores. We haven't a single core CPU. The frequency, we don't need high and high. So the trend is become slow and slow. Because the frequency become high and high, the need of electricity has become more and more. So the transistor can be more and more. Parallel APP performance can be become more and more. And the typical power watts for power we find in this period, the power is become the trend is slow. So this trend is the same as this trend. So if the frequency becomes this trend, the power becomes this trend. So we don't like high watts, high power. We like the power is become low and low. Because the power become low and low. The laptop, the life of laptop, the life of line battery are become low and low. So the power, we don't need the power become large and large. Okay, this is, we can see they stop getting faster. They stop getting faster. Okay, this is more important. Parallelism. As transistors get smaller, the power density stays the same. If Moore's law holds true, we also get a doubling of performance per watt every 2 years. This is another Moore's law. Manufacturers could reach the clock frequency between generations without more power consumption. And this stops around 2006. Too much current leakage becomes difficulty making transistors any faster. This is trend. Okay, now we find we can't make transistor faster. The speed of transistor is become very high due to current leakage, and because of that, we can't reliably make performance better by waiting for clock speed to increase. So the question is, how do we continue to get better performing hardware? So this is the question. This lecture gives solution for this question. Okay, domain specific hardware designed for a particular workflow or task. We can plan for a different work and the best case and make smarter design decisions for our average use. You can see do a few tasks but extremely well. So this is the better solution. Achieve higher efficiency by training the architecture to characteristics of is the CPU architecture. You can see higher parallel processing units used for graphics and image processing. So you can see GPU is another unit. CPU and the GPU. In the box, we only have CPU, but in current we have CPU and the GPU. GPU can accelerate the speed of graphic or image processing. So GPU is very important for the computer organization. So before 20 years, we don't think what is GPU, but in current, we can see higher parallel processing units for graphics and image processing, including video, including image, including graphics. So this is multimedia resources. So the processing speed of multimedia is very important for exam by computers. So some Chinese students like GPU, like video card to accelerate the video beam, the speed of video beam, the running speed. So some Chinese students asked me to buy some video card to increase the performance of computer, of GPU. So this is the need for Chinese students, some Chinese students. Okay, what if we want to improve general computing? We can see, please pay attention. This trend and this trend is become slow. So we can find this trend is become big and big. This is the number of cores.
Yeah.
So we can see this is one single core, two cores, 4 cores, and 8 cores. So the number of cores become big and big. If the number of cores become big and big, the performance becomes big and big.
Yeah.
So the number of cores is useful for improved general computing. So this is parallelism. This is the need of parallelism. Okay, this is great idea for parallelism. We can see parallelism has including software and hardware. We can see in this section parallel instruction. We can see one instruction at one time. For example, 5 pipeline instructions. We already covered this section, and we find the parallel request, parallel threads, parallel data, and hardware discriminations. So, if we had a dual-core CPU, we have a capability to parallelism. If we hadn't dual-core CPU, the parallelism isn't true. So parallelism is based on dual-core CPU. So parallelism is very, very useful. Okay, we can see section 2, parallelism and Flynn taxonomy. This is parallelism analog. I want to kill 100 potatoes as fast as possible. This is one example, one level. I can learn to kill potatoes faster, or I can get 99 friends to help me. If I had 99 friends to help me, we had 100 persons. If we had 100 persons, according to 100 potatoes.
Yeah.
So one person.
One potato.
Yeah, one potato. So this is parallelism. So parallelism is 并行工作。So you can find in airport, you can find the safety check, you can find the parallelism is very useful and normal. Anytime one result doesn't depend on another, doing the task in parallel can be a big win. Okay, classes of data level parallelism. We can see data streams and instruct streams. We can see single and multiple. So single and multiple is the two types of streams. Single instruction. So you can see single and multiple is 4 instructions. Single instruction or single data stream. We can see sequential computer that exploits no parallelism in either the instruction or data streams. Examples of SISP architecture are traditional unit processor machines. Everything we saw, we can see this is PU, this is processing unit, this is data pool, this is instruction pool. This is SISP. What is SISP? SISP is single instruction and single data. So, 单指令、单数据流 single and single. Yeah. If we have multiple instruction or multiple data streams, 多指令、多数据流 instruction and data, we like multiple. If we have multiple instruction or multiple data streams, we can achieve parallelism. So SISP can achieve parallelism. This is multiple instruction or single data stream. Yeah. This architecture extends multiple instruction streams against a single data stream for data operations that can be naturally parallelized. MISP is no longer commonly encountered, many of historical interest only. This is single instruction and multiple data streams. Computer that combines a single instruction stream to multiple data streams for operations that may be naturally parallelized. For example, SIMD instruction extensions or graphics processing unit. This is multiple instruction or multiple data. This is a better architecture. We can see multiple autonomous processors simultaneously executing different instructions on different data. MIMD architecture include multi-core and well-housed scale computers. So this is a parallelism. Okay, this is classes of data level parallelism. So this is SISP, SIMD, MISD, and MIMD. So MIMD is multi-core processor. Multi-core processor is our current processor. Okay, when parallelism fails, long chains of connected tasks do not perform better with parallelism. The analog is driving 10 separate cars can get 40 people somewhere faster than using a single car. But time to get one person to the location doesn't increase at all. We can't travel each meter of the distance in parallel. This is SIMD architecture. We can see data level parallelism is DLP. DLP can execute one operation on multiple data streams. The example is multiply a coefficient vector by a data vector. The sources of performance improvement have 3 sections. one instruction is fetched for Intel operation. Multiplication are known to be independent. Pipeline and currency in memory access as well. Okay, this is SIMD mode and scalar mode. This is some example. Okay, SIMD applications and implementations. Applications have scientific computing, graphics and video processing, big data, and gaming. Implementation have x86 ARM, RISC-V, and video card 24. This is some applications.
Single
You
instruction
can
multiple
see
data.
MATLAB, Photoshop, and deep learning. This has some types of applications. Yeah. This is first SIMD extensions. We can see it from MIT Lincoln Laboratories in 1957. This is Intel SIMD has been continuously extended. SIMD has continuous evolution. So from 1999 to 2010, you can see from SSE to AVX. This is the instruction set. And it has increased in size a lot. Intel, and you can find from 2011 to the future, you can find the register has become more and more. The size of CPU is become low and low. The instruction and the register, the number of register, and the symbol of memory, and the symbol of PCI interface. This is the trend. Okay, this is laptop CPU specs. We can see this is one example. This is from greater bit extensions overlap smaller version. You can see from 128 to 255. This is Intel SIMD data types. We can see in Intel architecture, it's unlike with RISC-V. The size of the word is 16 bits. It has a single precision SP, double precision SP. SIMD in the real world, today's compiler can generate SIMD code, but in some cases we get better results by hand. RISC-V vector hardware isn't widely available, so we'll study Intel's x86 SIMD instructions. Okay, you can see Intel SSE. This is for C programming. How do we use these SIMD instructions? We can see this is one example. Function calls that actually just execute an assembly instruction. This is some multimedia extension. You can see EPI 3232 is arguments are extended text intervals, each 32 bits in size. Okay, this is some instruction, some discrimination, some operation. This is x86 data type. This is some AVX code. This is some symbol for SSE. This is SIMD array processing from. This is pass-through code and SIMD and SIMD for one member and four member in array. Okay, we know. This is some example. This is 2 multiple 2 matrix multiply. It's simple. You can find this is A array, this is B array, this is C array. C array is the result of A multiple B.
Yeah.
So this is very simple for mathematics. But this procedure is for parallelism. This and this and this and this can calculate by 4 cores. So you can see in example, the 2 multiple 2 matrix multiply the result of C11, C21, C12, C22. We can divide the 4 calculating procedure. Okay, this is the 2 multiple 2 matrix multiply code. This is some C programming code. Okay, we know this is not important for this course, so we jump. Data level parallelism and SIMD. You can see SIMD wants translation values in memory that can be operated in parallel. Usually specified in programs as loops. So for loops is very useful in C programming. For loops, we can see this is the starting language, starting sentence.
Initial language.
This is the condition. This is the conditional condition. So this is the running sentence from loop and loop in every loop. So for loops is very simple and useful. How can we review more data level parallelism than is available in a single iteration of a loop? Okay. Looping in this file is this. We can see this is for assembler language. This is a function. This is loop. Loop unrolled. This isn't important. Okay, we can see this is generalizing loop unrolling. This is drawback to loop unrolling. Take a loop of n iterations and perform a k-fold unrolling of the body of the loop. We can see first run the loop with key copies of the body flower types. To finish leftovers, then run the loop with 1 copy of the body and for key types. Loop unrolling can greatly speed up your code, but isn't perfect for a couple of reasons. If you are doing it by hand, it's a really inefficient task. Loop unrolling increase your static code size. This is code optimization. Loop unrolling isn't really a form of parallelism, but is instead an example of code optimization. Code is converted from a form easy to understand to one with better performance. This is often the work of your compiler, but it may not always be able to make best optimization. Let's consider another example of how you can optimize your code. This is code optimization. Okay, let's see. This is loop invariance. This is one example of what we call a loop invariant. Invariant meaning does not change in the loop. What happens if f and g are expensive? then f and g are computed each iteration n times in total, but the loop will compute the result. Okay, this is some solution. Move the code outside of the loop and only compute it once, since it never changes. Okay, this is loop invariance. What happens if f and O or G is really expensive? We want to compute it as little as possible. Now we always compute it once, but what happens? We can see the solution is add a check to avoid computing it if we don't enter the loop. Okay, let's have a rest. Loop invariance. This is one example. Now we compute the impedance once if we enter the loop and otherwise not at all. This is one conditional sentence, n is more than 0. Okay, we can see lecture 21. How do we get more performance? We can't really do it by speeding clock up anymore. We can see parallelism is a good solution. Domain-specified hardware is needed. Single instruction, multiple data examples. Loop unrolling optimization is new solutions. So parallelism, you can search parallelism in search engine by or for stuff. So this in lecture 21, parallelism is very useful. So we must know some parallelism. In this lecture 21, we can see parallelism is become more and more, and parallelism is now effective technology. And in GPU, in computing, so the great idea for is parallelism. Okay, this is lecture 21. Okay, this is lecture 22. Lecture 22 is one law and the thread level parallelism. Parallelism has several levels. This lecture 22, has discussed thread level parallelism. Thread is the sub-level in processor. Okay, this is review for lecture 21. We can see this is the trend from frequency. If we want more performance, we have to come up with new solutions. So we stop being able to increase clock speed for our computers because the increased clock speeds will become more power, more typical power. If we want to increase the speed for our computers, we can increase number of cores. We can increase the frequency slowly. So the frequency the trend of frequency become slow and slow. The typical power will become slow and slow. And the transistor become more and more. The transistor is the need for the CPUs. So this is the trend. This is the full trend in transistor, parallel APP, and the frequency, typical power, and the number of cores. This is the trend. Okay, methods to increase performance. We can find the parallelism is very important. We can see instruction level, data level, thread level and the request level. This is 4 levels in parallelism. We can see instruction level and the request level. Who is the highest? Who is the lowest? You can find this is the highest, this is the lowest. So thread level is near lowest level. So thread level is very low. Okay, this is link taxonomy. This is SISB, SIMD, and MISD, MIMD. SISD is for single stage processor. Single stage processor, in the past, single stage processor can compute in some levels or in some channels. SIMD has 4 vector instructions. MISD is nothing really clear. MIMD is for multi-core processors. Okay, this is great idea for parallelism. This course, this lecture 22 is talking about parallel threads. You can see parallel threads, parallel requests, parallel instruction, parallel data, and hardware descriptions. So parallel threads assigned to code, for example, lookup, X is lineage, parallelism, and archive high performance. This is hardware. This is the warehouse. The scale of computer of warehouse is large and large. The computer has multi-core and memory, input and output. In the core, you can find the instruction unit, function unit, and the cache memory. In this cache, you can find this is logic gates to archive this section. So, computer has several levels. Is correct. Okay, this is lecture 22, the agenda. In lecture 22, we had studied parallel computing, parallelism, challenges, and synchronization, OpenMP and OpenMP work sharing. This is the agenda. Okay, this event is from lecture 21. This is the important content for MIMD computing. So from frame taxonomy, MIMD is multi-core processors. Okay, we can see how do we apply parallelism to processors. Goal is make computer faster by performing tasks concurrently. The solution is one is use multiple cores to run multiple tasks in parallel. 2 is run multiple tasks on a single core concurrently. So the solution is very useful and effective. You can think multiple cores. Multiple cores according to multiple tasks is very one by one. Yeah, one task by one core is idle, is effective. One task for single core concurrently is also useful, but the one solution is useful than the solution 2 because we have a multiple cores. If we have a single core, we must use the solution 2. How do we apply parallelism to processors? The goal is to make computer faster by performing tasks concurrently. The solutions: 1 is use multiple cores to run multiple tasks in parallel. So this is important solution in lecture 22. you can see software task is processes. Processes and thread. Processes is including several threads. So processes is large than threads. Program is compiled, assembled, and linked code that's ready to be loaded and run. A process is a program that's currently running on a processor. The process has a PC and a memory space. This is process and program. This is there are different from program and process. Okay, this is process state diagram. In operating system course, you can see process state diagram 2. We can see in this image, we can see this is waiting for input or output or event.
Ready, running, waiting. Yeah.
You can see there are 1, 2, 3, 4, 5 status. One is new, one is ready, one is waiting, one is running, and one is terminated. Yeah. If we have a new one process, we find this status is active. We can convert it to process, and the new status can become to ready. And when the schedule dispatch, the ready status becomes running. If we have some interrupts, the running status becomes ready. What is waiting? The waiting is waiting for CPU. So if input and output or event waiting, the waiting status is active. Terminated is one termination. Yeah, we can see reclaim resources, destroy process.
After the process done, it will destroy.
Yeah. When the process are terminated by some advanced process, for example, system process can kill the user process. The terminated is the exist of process state diagram. So we can find that this is the input, this is the output. So this is waiting for input or output or event, the diagram. Okay, this is some resources, some work file from URL. Okay, multiprocessor systems. We can see this is processor 1. This is processor 0. This is processor 1. There are 2 cores, or there are 2 processors. There are 2 processors, but there is one main memory. Yeah. So main memory is shared for processor 1.
Shared memory.
0. So you can find this is input, this is output, this is I/O to memory interfaces. From the interfaces, we can see the main memory can transmit data to input and output. Yeah. So the main memory is in the middle, in the center of the multiprocessor systems. So this is multiprocessor. We can find if we find the processors aren't enough, we can add more processors in the multiprocessor systems. If we have more and more multiprocessors, the capability of systems can be increased, but the cost can be increased. So the cost is more important factors we must think. Okay, multiprocessor systems, we can see the discrimination. A computer system with at least two processors. You can see at least two processors or cores. One is each core has its own PC and registers. PC is one register.
Yeah.
Each core executes independent instruction streams. Processors share the same system memory. System memory is main memory. Communications through loads and stores to a common location. Yeah, this is that there are four points for multi-processor systems. We can deliver high throughput for independent jobs, but task level parallelism. Okay, this is a multi-processor example. We can see run craft and mine craft are simultaneously. Craft and mine craft is the applications. Craft is one explorer. We can see each are separate programs. Each has a different memory space. Each can run on a separate core. So this is important. If we have several processes in CPU, we can divide some cores to process the applications. One application to one core. If we have 8 cores, we can running 8 applications simultaneously. So you can see, don't even need to communicate. This is for applications. This sentence is mean. Each applications haven't communicated each other. Every core is for every application. So the application can be running differently.
From different memory space.
Yeah. So the main memory is shared. This is the basic of multi-processor example. We haven't enough main memory for single use. We must share main memory. Okay. This is multi-processor. We can see multi-threading. How do we apply parallelism to processors? We can see the goal is make computer faster by performing tasks coherently. The solution 2 is running multiple tasks on a single core coherently. You must focus single core. So thread is for single core.
Yeah.
But in multiple core CPU, we can use thread at same time. So thread is good solution for single core or dual core. Okay, software comes in threads. In Chinese, we call threads 线程. Yeah. Yeah, thread is this. We can say thread is unit of execution within a process. We can so far have a single thread. We have a single thread of execution. We are single threaded. But a single process could have multiple threads. This is the solution. One process can be divided multiple threads, so the parallelism can be achieved in single core. If we hadn't thread the single core, is 1-by-1 process. If we have 1-by-1 process, the single core computers have lower performance. If we want to have more and more performance in single core computer, we must divide the process to multiple threads. This is very useful. So multi-thread is software task. Okay, this is thread memory. We can see thread have separate PC, separate registers, separate stack memory. Thread share code memory, static memory. So you can see this is the dividing. This is the share. This is single threaded process. This is multiple threading process. Multiple thread. This is single threading. Single threaded process. The performance of single threaded process is lower than multi-threaded process. This can have one core, but there are threads. This has one core, but they have one thread. Yeah. If they have one thread, the performance isn't high. Okay, this is thread example. Let's see. You are implementing crime. Crime is one explorer. You want a tape for each web page you open. The crime can open multiple tapes. The same code loads each website. We can see this is shared coding code section. The same global settings are shared by each tape. It is shared static section. Each tape does have separate state for things happening locally through. This is the separate stack and registers. So actually, browsers can use separate processes for each table for a variety of reasons, including performance and security. So each table has each thread is good because each table has a shared code section, shared static section, separate stack, and separate registers. So tapes can run differently, disparately. The task running divided and the tapes running. They are not communicated. So each tape can running. Each table, if one table is dead, we can kill the table disparately. So this is the thread, the use of thread, and the good things of thread. Okay. We can see this is multiprocessor and multi-threading. Yeah. Please, if you have time, please look at some parallelism from search engine and thread and process. Thread and process you can see in operating system course. You can learn some details in OS. Yeah. Thread and the process is very useful for our computer, for our CPU. So thread is a good solution. Okay, today is enough. In next Tuesday we are going. Okay.